Hi, I'm Greg Livingstone. Thank you so much for joining. Today, I'm going to be talking about hydraulic oils and specifically some innovations we have in measuring and managing these fluids. So I will first talk about how hydraulic oils fail, why we care about this, how it actually impacts profitability, what the biggest problem that we have with hydraulic oils today is, which is probably the most important takeaway, and then also talk a little bit about some solutions that we have. Starting off with a couple definitions. Hydraulic oil, I think if you're here, most of you probably know what this is. Basically, it's a fluid, and this medium is used as a way to transfer power from one place to another in a hydraulic system. How they degrade is that even before they actually go into service, there is a chance that hydraulic oil may start degrading, just sitting in drums before it actually goes in your system. However, once it goes into use, it's exposed to a lot of contaminants, heat, and all sorts of other stressors that cause it to change physically and chemically. And ultimately, the reason we care is that this will adversely affect the performance of the fluid. In many other applications, as oils degrade, there's lots of different manifestations of this. So you may have an increase in viscosity or in acid number. In the case of hydraulic oils, the predominant result of fluid degradation is varnish. So what do we mean by varnish? Well, there are literally dozens of different chemistries that make up varnish, but really this is a catch-all term that means it's an oil-derived deposit. It's a deposit that's settled somewhere out in the internals of the lube system that's come from the oil. And what the chemistry of this deposit is really depends on three different things. It depends on the operating conditions of the machine, what type of oil we're actually dealing with. So in other words, what are the additive components, what is a base stock, and what other contaminants have ingressed into the system that may alter the degradation pathways. So a few different mechanisms that we see in hydraulic oil degradation. By far the most common one that we deal with is oxidation. Virtually anything in the presence of oxygen has the ability to either donate or transfer an electron, causing the oxidative process to begin. Essentially, it's a formation of a free radical that will continue to react and react and react until something quenches that and neutralizes that free radical. That something is antioxidants, and it's why antioxidants are such an important ingredient in any lubricant that's used in an oxidatively stressful environment. One of the cousins to oxidation is ultraviolet radiation. This is of particular concern if you draw an oil sample and then put it outside in the sunlight for a period of time. It may be exposed to UV degradation prior to getting to the lab, influencing the results. A little bit quicker, more sudden, rapid form of fluid degradation is thermal degradation. And this is when we have a very, very high temperature that cracks the backbone of the lubricant. Typically, we're looking at 300, 350 degrees C and higher, so very, very high temperatures. And typically, these are more events. So in hydraulic systems, one such event may be electrostatic spark discharge. Another could be the implosion of air bubbles, known as microdieseling, creating a coke-like tiny submicron piece of carbon material. And another challenge we see in some hydraulic systems, if the valves are not set properly, you could have a very high amount of flow going through a tight surface in the valve, causing extremely high temperatures in the valve body, which can be also a form of thermal degradation. On top of this, we have all sorts of contaminants. And really in the world, there's three types of contaminants. There's gas, solids, and liquids. So we could have water that gets into the system. We may have gas that ingresses into the system. And we could have solid particles, some of which are catalytic. So in addition to all of the deleterious effects that these contaminants can have on the system, they also can speed up or accelerate, act as catalysts to how that fluid degrades. And then finally, we have, in some cases, we've seen additive dropouts, and the biggest challenge that we have seen of late is compatibility. So if you are mixing, say, a synthetic oil on top of a mineral oil, some synthetics and mineral oils do not play well together, and even some mineral oils and mineral oils do not play well together. So don't assume when you put two different products together, you will have full compatibility, and that's something to be aware of as well, the result of which certainly can be oil-derived deposits. Hydraulic systems are under more stress today, and this, I think, is a common theme that we see in many, many different applications. But in the world of hydraulic oils, in particular, we see these hydraulic systems are generally getting smaller in size. The reservoirs are getting smaller. The temperatures are higher. The flow rates are higher. So then, therefore, with a smaller reservoir and higher flow rates, we have less residence time and less time for air bubbles to pop and come out of the fluid, for contaminants to settle down to the bottom. Filtration is very, very important. We've recognized this in the hydraulic system, so we have extremely tight filtration. In some cases, this may in fact be detrimental and could cause electrostatic spark discharge. And another trend that we're certainly seeing in the hydraulic market is that leaks can cause both a safety and environmental hazard. And so a lot of focus has been gone into fixing leaks and having a good leak management system. Well, that's fantastic, except now you're no longer refreshing the oil on a regular basis with new oil and continuing to refresh with new additives. So now that original charge of oil is going to have to perform longer in a more stressful environment. And finally, as our economy becomes more and more global and there's more global competition, we see productivity schedules we're looking at around-the-clock operations, less downtime, and therefore less opportunities to take care of your hydraulic system. So why don't we care about how hydraulic oil is degrading anyway? Well, it can be very, very costly for an operation. So as an example, I'd like you to just see this little time lapse of a mine. You'll notice these three excavators here that are in the middle of the screen that are working away and filling up these haul trucks. Well, these excavators are typically supported by between 5 to 10 different haul trucks, depending on how big that haul truck circuit is. And if one of these excavators go down, we're looking at between $5,000 to $10,000 an hour. And basically, not only do you have several haul trucks that are out of commission, but you also have a lot of ore that can no longer be mined. So these are pretty hydraulic intensive systems, and hydraulic failure can be a challenge in these systems. But this is just one example of how hydraulic oil failure can in fact have an adverse effect on your productivity. Luckily, we have tests available to be able to measure the changes, the physical and chemical changes we see in the lubricant. So some of the key parameters or characteristics that we want to look for in an oil analysis test for hydraulic oils: viscosity is clearly one of the most important ones. Contaminants, how the fluid interacts with contaminants. In other words, if there's water, does it mix with the water? Or if there's air, does it create foam, or does it create poor air release properties? So how the fluid actually interacts with contaminants is important. Chemical changes to the fluid, and oil degradation. And so if we look at this and we're understanding hydraulic oil failure, in the oil analysis side, I think we've actually done a really good job on contamination. So we understand how to measure dirt and have understood this for some time in hydraulic systems, water, and how to monitor that effectively, and certainly air. So we have that down from an oil monitoring perspective. However, now we're coming to the most important point that I want to make. Is the number one issue that we see in hydraulic oils is, in fact, we have these fluids that are failing due to a degradation. However, we're not actually running the right tests. So the oil degradation side, luckily we actually have tests available that are very, very useful, and we've applied in other, in various other verticals. So we know how to measure the varnish potential of the fluid. It's just not routinely done in hydraulic systems, even though one of the modes of failure is the formation of varnish and deposits. I love this quote by Edward Deming. "You can't manage what you don't measure." Clearly that is relevant here in our discussion of hydraulic oils. If we know the fluid is failing due to oxidation and degradation and we're not measuring this, how can we possibly manage this? There's also another quote that he made that I also love, a little bit sarcastic. He said, "Change is not necessary because survival is not mandatory." I love that. MPC test is something that we know does a fantastic job. And if you look at the ASTM D7843 method, the first thing you will notice is that it's actually a standard that's created for turbine oil. And although that is true, the genesis of this test was a colorimetric test that was developed by Dr. Sasaki in Japan, where literally he has tested this in over 10,000 different hydraulic oils. So the genesis of the MPC test, in fact, has been used very successfully in hydraulic oils for years, and certainly is very, very relevant. So essentially the MPC test, it's a fairly simple test where you mix a little bit of oil with a little bit of solvent, you filter it, and then look at the color of the patch. And if the color is dark, that's not so good. If the color is light, then you're in good shape. One important fact to keep in mind is that the color of the oil is not necessarily indicative of the color of the patch or the varnish potential. So even if the oil looks nice, clear, bright, not very dark, you could, like in this case here, have an MPC of 37, or you could have oil that literally looks like engine oil with a low MPC. One thing for those of you that are in the testing world and are running MPC tests and are looking at doing MPC tests for hydraulic oils, we recommend the same testing procedure. However, there's a couple other things that may make sense for you to measure and monitor here as well. So typically we will report the delta E, the total amount of color that's analyzed on the patch. The other thing that is of value is to report the actual volume of sample that made it through the patch. So in the world of turbine oils, virtually all even severely degraded turbine oils will make it through the patch. In the case of hydraulic oils, sometimes we see fluids that are so severely degraded or contaminated that it will block the patch. And so actually measuring how much of that fluid makes it through the patch is certainly of value, and how long it takes to filter. If it takes 30 seconds or 15 minutes, clearly there's a difference between those two samples. One other thing that we have found that can be very important is actually weighing the patch before and after, and the gravimetric analysis of that patch can also provide some really, really good information on the condition of the fluid. So just an example here of how we may report 3 different MPC values, all with a MPC of 45. So typically anything over 40 would be considered critical. So we have 3 critical fluids here. The first case, we have an MPC of 45. All the fluid made it through the patch in 30 seconds. Now, compare that to the last case here, where only 30 mils made it through the patch, and it took us 15 minutes. So clearly there's a pretty significant difference in contamination and degradation, and this allows us to better differentiate. And just for a real life example, this is a case, this hydraulic system actually had an MPC of 9. You see the patch, nice and light. However, only a tiny bit of this fluid actually made it through the patch. Only 15 out of the 100 mils made it through the patch. Then there is actually a thick layer of basically colorless residue that had formed on this patch, and in 15 minutes. So this is another good example. This was from a synthetic fluid, and maybe a little different mode of degradation than we sometimes see in mineral-based hydraulic oils. Nonetheless, it's still a good example of the value of adding these extra reporting procedures onto the test. Let's talk a little bit about solutions. So the most important thing is we need to be actually testing and measuring and monitoring varnish potential in the fluid. What happens if how do you actually manage this now that you have a high varnish potential? Well, any of you that have spent some time either working in the energy industry or working for customers in the energy industry are familiar with the varnish mitigation technologies. These are prevalent in power generation, petrochemical, air separation operations, and there's several different technologies available in the market. There is ion exchange resins, depth media filter systems, electrostatic oil cleaning, and in the right applications, these technologies can do a really good job. They are not ideally set up for hydraulic applications in many cases. In some cases, it may take some additive components out. In other cases, it may have the viscosity may be too high for the technology to deal with. But in all cases, the cost to treat, say, a small hydraulic system, a couple hundred liters or a drum of hydraulic fluid would be very, very, very high if you wanted to have a dedicated filtration system on. And so for many hydraulic systems, we need a little bit more scalable solution. So that brings us to technology we've developed called Solvencer, and this is basically the name of the technology that actually goes into several different products that we have, such as Decon, Boost VR, or Boost AW. AW stands for anti-wear. So we have several different products that actually incorporate this technology. This is a solubility enhancer, and so you may be able to kind of guess where we got Solvencer from, solubility enhancer, but essentially what we're doing is increasing the solubility of the fluid so that the oil degradation products actually can come out of solution and stay in the oil. And if you actually put this into a system that is severely contaminated, it allows oil degradation products, varnish and sludge, to actually dissolve back in the oil. So you can actually clean the system up by increasing the solubility. One of the benefits of using Decon is that it is simple and risk-free. You essentially add this in at a 3 to 5% treat rate. You pour this directly into the reservoir while the system is operating, and it immediately goes to work to prevent any further varnish from forming in the system and to dissolve varnish that's already settled in the system. And because there's no surface active chemistry, there's not a risk of contaminants collecting somewhere and maybe getting pushed through a servo valve or any other adverse effects that you may see with detergent dispersant type cleaners. So it also has a wide range of compatibility. So virtually any Group 1 through Group 4 hydraulic oil, either ashless or ash-containing ZDP type additive components, are fully compatible. So it's very simple to add in, and it's a little more scalable. So if you have a 5-gallon hydraulic system or a 5,000-gallon hydraulic system, it will have the same kind of cost. Now the fun part. We're going to look at a couple case studies where we've used the Solvencer technology in the field. This first picture here, we don't necessarily see hydraulic oil contamination problems, but there is a rag right where this mobile piece of equipment is rotating here at the bottom of the screen. Maybe someone talking about grease can do a case study on the contamination in this particular system. But we're going to talk about varnishing issues first in a forge press, and this is a fairly large forge press. There are 4 different reservoirs, each with about 12,000 gallons, and each of these reservoirs powered 1 cylinder. And the operation noticed a decrease in ram speed, and their oil supplier did some sampling for them, identified a very high varnish potential, and sure enough, after inspecting the system, they found evidence of varnish in the manifold and several other components throughout the system. The varnish potential also was quite high. So this was something that was concerning to them. They ended up putting 3% Decon into the fluid. And within a week, the varnish potential was lowered, and they also, a month later, had the opportunity to actually inspect some components and saw some very, very heavily varnished components looking somewhat clean and looking like the varnish had actually been dissolved. Most importantly, they noticed a ram speed was increasing and more consistent, and they no longer had sticking valves. So just a trend of kind of how this looked over the last several months. The varnish potential in the first week went from 53, an MPC of 53, down to 6, and has been then maintained ever since in less than 15, so in the normal range. So I think that was a good case study, and certainly a lot more efficient than adding filtration technologies on, and certainly worked very well in this case. So the plant is. A key part of this is that there's no silver bullet that will solve everything and allow you to now ignore the fluid. So condition monitoring continues to be an important aspect of this. The plant is doing regular testing and trying to now do a little better job in monitoring the health of the hydraulic fluid. As a top-up fluid now, they are also adding the same percentage of decon to the new fluid that's added to the system to maintain that 3% level of decon. Next case study I want to touch on is plastic injection molding. So this is from a leading consumer manufacturer using a Millicron 1,000-ton extruder, and they started. They had noticed lots of deposits in several of their machines that every time they changed a filter or looked at any internal component of the system, they saw this brownish, gunky, sticky deposit. And they also had some actual performance challenges. So the first thing is their heat exchanger actually didn't work. The fluid was not flowing through the heat exchanger. And then secondly, once they shut the machine down, when they went to start the machine up again, everything was sticky, and it took a long time to actually get the machine up and running. And so it actually did cause significant delays in machine operation. So there were actually not just brown sticky components, but actual impact of varnish. So in this case, we put decon in at a 5% treat rate. A couple hours later, through testing, we identified the varnish potential was brought back to normal. And then long term, we've seen very, very good results. So the most interesting thing is that within 24 hours, this heat exchanger that basically was not working and hadn't worked for several years, now fluid started flowing through. So they actually had to adjust the heat exchanger, but now instead of running the oil at 140 degrees, they're actually able to run the oil between 95 and 100 degrees. So just that in and of itself is reducing the stress of the oil by about 4x. So in other words, you're providing about a 4x improvement to the life of the oil. The other thing that's they've noticed that they're grateful for is that their mornings are a little more chill. It's easier to get the machine up and running, and as soon as they hit on, there's no sticking valves. Everything starts up as expected and on time. So they've also noticed the mold clamp speed has increased, and ultimately this will translate to a higher production yield as well. So to summarize, oil degradation and varnish is a common mode of hydraulic oil failure. It's we know that it's a pretty significant issue in hydraulic oils. Please run MPC tests, and just now that you have seen this, you have no excuse. You can't just stick your head in the sand and just say, okay, my normal oil analysis says everything's fine, I'm good to go. Now that you've seen this, you have no excuse. You should be running MPC tests on your hydraulic fluid. And secondly, Solvencer is a solubility enhancing technology. It's a little more scalable than traditional varnish mitigation systems, and in hydraulic oils can do a really good job of providing a protection to that fluid to improve the deposit control properties of the in-service fluid, and also does a good job of decontaminating the system and dissolving sludge and varnish that's settled in the system. Thank you so much for listening, and very much appreciate your attention.